Okay, let's look at some Gaussian elimination least squares practice problems. So let's start with a simple one, so 2 by 2, actually back from chapter 5. Let's do Gaussian elimination with pivoting. So let's solve this system. 2, 6, minus 3, 0, x1, x2 equals 0, 3. Solve this with pivoting. Okay, so hopefully you can easily find the pivot, and then you can find your shear matrix. If you didn't find your shear, make sure you did that as well. Okay, so our matrix starts like this with pivoting. We want to take the largest absolute value item in the first column and make that our pivot. So we swap two rows. And now we want to solve this with our shear. And I'll show you the shear in a second. But after that, we're going to shear it into this form. So again, remember that our shear, in whatever we want to do, is for the row we want to shear away, we're going to take that value divided by minus the value of what we're going to leave. So we're going to take 2 divided by minus 3, so we're going to take 2/3, and that becomes our entry for this shear item. Okay, when we multiply that by this, we get minus 3006, and for back substitution, this is trivial. We just divide through and get a half and 0. Okay. Now let's do higher dimensional stuff. Let's look at the determinant of our of a 3 by 3 matrix, and then answer what is the rank of this matrix A. Okay, so hopefully the determinant was easy for you. I'm going to write it out here. As again, we just copy the matrix over, and so our determinant is just the first value. Could have done this row as well. 3 times 2 times 1 is 6, minus 3 times 0 times 1, which is 0. Plus 0 times 0 times 1, which is 0, minus 0, 1, 1, which again is 0, plus 1, 1, 1, which is 1, minus 1 times 2 times 1, which is 2. So overall, I have 6 plus 1, which is 7, minus 2, which is 5. Our determinant is 5. And then the rank of the matrix, well, if the rank of the matrix is non-zero, then we know the matrix is non-singular, it's full rank, so this is 3. Okay, so now let's go solve a system. Want to solve this system AV equals B, where here is A and here is B. And I want you to go ahead and solve that. I've actually shown you the solution vector here, so I'm giving you a few hints to check along the way in case you get stuck with it. Start with this, do some steps of Gaussian elimination, come up with whatever you need to do, and then pivots and shears and whatever, and get to your triangular form, which should look like this. Okay, so hopefully you could look at this and say, oh, look, 0 is in the first place. I have to do a swap. And after I swap that, I'll have 1 and 0. And now I can go ahead and try and eliminate that. But I also have 0, 0 here. So I'm going to swap this all the way down the bottom. So I'm going to swap a second time. This gives my second swapping matrix. And now I'm going to go ahead and have this matrix, and I want to do my shear. My shear matrix is then going to be 1, 0, 0, minus 1, 0, 0, because it's 1 divided by minus 1. That's going to be my item. The last item is 0, so I can leave that one alone. When I multiply that out, I get this is my new matrix, which I can back solve and get this for my solution for V. Because 1 minus 1 gives me that. Put the minus 1 in, I get 0, and then minus 1 for the top item. Or sorry, 0 for the top item. Okay, let's do Kramer's rule in 3D. So let's see how to apply Kramer's rule. So here we have our matrix on our right-hand side. Go ahead and apply Kramer's rule in 3D to solve it. So hopefully remember that, in fact, in the general form in ND, Kramer's rule, the first part of our solution is the determinant of the cofactor A1 divided by the determinant of A. The second one is the determinant of A2, where each of these items are going to be where we remove that column and put the right-hand side in place of it. So we're going to need a couple of determinants. So for the determinant of A, we're just going to have the determinant of 301, 1, 2, 0, 1, 1, 1. We've already done this determinant earlier, right? We just get 6, and we get a 1 and a 2, so we get 5 overall for our determinant. For these other matrices, so here we can see we took, for A1, we replaced the 311 with 866 and leave the rest of the matrix alone, so we get 866, 0, 2, 1, 101. Sorry, I was reading the columns. So now when I go to do my determinant, I'm going to get 8 times 2 is 16 minus 8 times 0, so that's just times 0, plus 0, 0, 0, so that's going to give me 0, minus 0, 6, that's going to be 0. And then here I'm going to get plus 1 times 6 times 6, so I have plus 6, and here I'm going to get minus 1 times 2 times 6, I'm going to get 12. Overall, that gives me 16 plus 6 minus 12, which gives me 10. For our second determinant A2, I replace the middle column with the right-hand side, so I get 311, 866, 100. I'm not going to go through the determinant again. This also has a determinant of 10. It doesn't have to. It could be something very different, but it just happens to work out to 10 here. And then for the third A3, I take the last column and I replace it with the right-hand side, and I get this matrix, who again just happens to have the determinant of 10. So the solution for this problem is 2, 2, 2, because it's 10 divided by 5, 10 divided by 5, 10 divided by 5 for each of the items. So Kramer's rule in 3D. Okay, now let's go do an even higher dimension. We're going to go to 4D, and we're going to do Gauss elimination without pivoting. And we're going to denote this system by AX equals B, and just to make it easier in the description here, I'm going to carry around in the augmented form instead of keeping to do multiplying by both sides. It's easier to just view it as a bigger matrix. Besides doing Gauss elimination in this case, I want you to also come up with the LU decomposition. So I want you to do both Gauss elimination and compute the LU decomposition. I want you to do it at the same time, and if you remember from the reading, hopefully that'll be easy for you to do because you know how they're related. Okay, so that was a bit of work, but hopefully you're now done. Let's walk through so you can check your solution. So here's our augmented matrix. So the first thing we want to do is eliminate x1 from these items here. So my multipliers are going to be, I'm going to write the multipliers here. 4 divided by 2 is 2. Minus 2 divided by 2 is minus 1. And 4 divided by 2 is 2. Now when I'm going to put them in the shear matrix, I actually want to use negatives of these multipliers, but I'm going to use these multipliers because that's how I get to the LU decomposition. So it's sort of the negative of the sign of the items I'd put in my shear matrix. After I multiply this by my matrix, I get this new intermediate form. So now I have to shear to get rid of the 6 and the 9. Shearing to get rid of the 6 and the 9, I'm going to use 6 divided by 3 gives me 2. 9 divided by 3 gives me 3. These are my multipliers. Again, my shear matrix, I put in the negatives of those, multiply that out, and now I get my final form. To get rid of this the last item down here, I'm just going to use minus 1. And solving that by back substitution, I can then solve my entire solution. So 6 divided by 2, take the 3, stick it in here, work your way back up the matrix, you get this as your final solution. Now, as I said, I was doing this where I use these multipliers, which are the negatives of the items I put in when I do my shear matrices. And I did that because now it becomes easy to do the LU decomposition. I put all of those multipliers in this lower triangular form. If I go back and I look at my shear matrices, you'll notice I already had them in those sort of locations. I'm just putting the negatives of those together. And that gives me my L matrix. And L times U, where U is the result of our triangularization, L times U gives me back A. So the positive sign versions go into the LU decomposition. The negative signs are what I use to get here. And so that gives me both the relationship between Gaussian elimination and the LU decomposition. Okay, let's go do a least squares problem or two. So let's be given these 5 points, P1, P2, P3, P4, P5. Sorry for putting them in the wrong order. Find the least squares approximation of these using the best straight line you can. So give a straight line approximation, doing least squares. Okay, so hopefully that was pretty easy. If I write that in matrix form using, say, the explicit form of the line, I'm going to have AX1 plus B equals X2. I could write another form as well, but this one works fine. For this problem, so I have two unknowns, A and B. So here's my x2, here's my x1. So x1, and then my b comes on this side, so I just rewrote the function this way, subtracting stuff out. Given that I call this a, now I can multiply both sides by a prime. So I get a prime times a, and that gives me the equation 19,115. AB equals minus 4, 1. So that gives me my normal equation, and thus the least squares solution of this line is just solve this with Gauss elimination, or your 2 by 2, whatever you want to solve it for. And if you want to do this, take these data points, go out and sketch them, and you'll see that this gives you the best fit to the line. So those are examples for some basic linear systems and some least squares. We'll see least squares again when we get into SVD. If you had problems with any of these problems, take the examples from the end of the chapter, work through them until you can do it without looking back in the book, just either by knowing the formulas or looking at your notes.